Hi, today I'm going to talk to you guys about a thermodynamics concept. It's one of the basics and intros to Thermodynamics 1 and also Fluid Mechanics 1. It's the concept of the U-Tube Manometer, and I'm going to be explaining to you guys a few concepts related to the U-Tube Manometer, and also I'll give you guys a small example at the end. So the first subject that I want to talk to you guys about before moving on to the manometer example is pressure. Now, pressure is usually defined as the force per unit area. Now, the equation here that we use for fluids is pressure is density times gravity times the height. So this again is density, gravity, and height. This is the equation that we're going to use for pressure when we are solving in the U-Tube manometers. Now the next concept is actually a material property, which is specific weight. And specific weight is defined as the weight per unit volume. Per unit volume. Now, from that definition, you'll probably assume that the equation for specific weight, which we'll just denote as SW, is weight, which is mass times gravity, over volume. Now, if you notice in this equation, we have M for mass and V for volume, which is actually just density. So we can simplify the equation as specific weight is density times gravity. Now, the third and final topic I'm going to talk to you guys about before the example is another property called specific gravity. And it's basically defined as the ratio of two densities. Alright, and it's denoted with the symbol gamma, when it's equal to rho 1, or density 1, over density 2. Now in Thermodynamics 1, and also the example that I'm going to show you guys next, we usually use the second density as the density of water. So we're just going to assume from now that rho 2 is rho of water, and we're going to assume that it is 1000 kilograms per meter cubed. Now, I'll show you guys an example now about the U-Tube manometer. It's one of the basic ones that we'll go through. So, a U-Tube manometer, U-Tube manometer is a device that's used to measure small amounts of differential pressure. Now, I'm going to show you guys what a U-Tube manometer looks like with a basic drawing. I know my drawing's not that great, but it is a good enough, adequate representation of how it would look like. So now here's our U-Tube manometer. It's a very basic drawing. So now what we need to do in this example is to find the pressure at B. Alright, so what we need to do is the pressure at B, let's say each color represents a different fluid, and we know that the pressure at A is 2 bar, and the conversion from bar to Pascal is 1 bar is 2 times 10 to the power of 5 Pascal. So that's the conversion. And so we have the specific weight of oil. That's there. Now we can easily convert that by doing specific weight is rho of oil over rho of water. And like I said before, we're going to assume that rho of water is 1000. Now if you substitute 1000 for rho of water and 0.8 for gamma, we get rho of oil is 800 kilograms per meter cubed. Okay, now the next thing we have is we have another substance here, which doesn't really matter what it is in this case, because when I defined the U-Tube manometer, I said that it measures the differential pressure. Now the differential pressure from this point here and this point here is going to be 0, because the height from here to here and here to here is the same. Well, approximately the same, because this is supposed to be a straight line, but my drawing is a disaster. But it should be the same height. Now, if you have a continuous fluid, same fluid, and it's reaching at the same height, then the differential pressure will be 0. And I can prove that to you because the pressure at this point here is going to be rho times g times h. Then it's minus, or let's call it h1, minus rho times g times h2. Now here h1 is from here until here, and it's equal to h2, which is here until here. So if h1 and h2 are equal, and it's the same fluid, so rho is the same, and so is g, and h is the same as well, which means it's going to be equal to 0. Which means we can simply say that if we have a continuous fluid reaching the same height, we can easily say that the differential pressure between these 2 points is 0. Which means that when you write our equation to find pressure at B, we can neglect this fluid entirely. But if the drawing was different, and if it was like this instead, and say we had a fluid here that goes all the way up here. Now these heights, h1, which is this, and h2, now h1 is greater than h2. So now what we can do is, if we're trying to find the differential pressure between this point and this point, the continuous fluid continues until this point here. So this height, let's call it h3, is the same as h2, which means that the differential pressure from this point and this point is going to be 0. Which means that the pressure here at this point, at the top, is going to be rho times g times h1 minus h3. But that's in a different case. So now back to our main example. Let me just erase this really quickly. Alright. Now back to how we solve for pressure at B. So now we have to write the equation for pressure. So we have pressure at B is equal to, now this is going to be a long equation, but essentially it's the same equation for each different fluid. It's going to be rho of this first material, which is oil, let's start off on the left, times G times H, let's call it H1. Then, as we're moving down the manometer, we're going with gravity. Now when we're going with gravity, we add the next pressure. So the next pressure is going to be this continuous fluid, but as we've established already, is that the differential pressure from this point here and this point here is going to be 0, which means that we can neglect this fluid's pressure entirely. So then the next thing we need to do is we need to subtract the pressure that's created by this substance here, which is water. So what we need to do is subtract rho of water times G times, let's call it H2. Alright. Then the next thing we need to do is we need to go to this pressure caused by, let's call it oil number 2. So minus rho of oil 2 times G times H3. Now we need to do this for the next fluid as well, which is air. So we subtract again rho of air times gravity times H4. Now we've reached pressure at B. So the next step is to substitute the values that we have. Let me do that down here. So pressure at B is equal to rho of oil, which is this one, which we found as 800. It's 800 times gravity, which is 9.81 meters per second squared. Now H1 is going to be the height from this point till this point, which is going to be 70 centimeters or 0.7 meters minus rho of water, which is 1000, times gravity, which is again 9.81, times height 2, which is 0.4. And it's 0.4 because the water is this region here, from here until here, which is 40 centimeters height. Then the next thing we need to do is do the same thing except for oil too. So it's going to be here, this is specific weight, so we need to convert this into a density, and we follow the same procedure as we did over here. So instead of 800 for this one, it's going to be 750 kilograms per meter cubed times gravity again, times 0.3 minus, now the next one is rho of air, which is 2.5 times 9.81 times 0.5 meters. Now actually I forgot one thing, which is pressure at point A, which we add, and like I said, to convert from bar to Pascal, 1 bar is 1 times 10 to the power of 5 Pascal, so here we'll have 2 times 10 to the power of 5, which means that our answer for pressure at B is 199,358.46 Pascal. Well, that's how you basically solve the U-Tube manometer. If you guys like, leave a comment below and I'll solve another example, or simply give me more ideas, any video ideas you guys have. And thank you guys for watching.